In Chapter 6, Section 4, we're going to be looking at the quadratic formula. The quadratic formula is a formula that is used to solve a quadratic equation in standard form. A quadratic equation in standard form means that you have the x squared, the x, the constants all on one side of the equal sign equal to 0. Looking at our first example, x squared plus 5x plus 2 equals to 0. A is 1x squared. B is 5. C is 2. And the quadratic formula, there are several different little mnemonics on how to have it memorized. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And this needs to be memorized. For the test, x equals the opposite of 5 plus or minus the square root of 5 squared minus 4 times 1 times 2 all over 2 times 1. Our orders of operation tell us that we do what's inside parentheses or any grouping symbol, and this radical is a grouping symbol. Negative 5 plus or minus 25 minus 4 times 1 is 4 times 2 is 8 over 2 times 1, which is 2. Negative 5 plus or minus 17 over 2. 17 is a prime number. Final answer. That's our 2 plus and minus the radical. The next example I want to do is one where we're going to have to simplify after we get our answer. I do notice that I have a quadratic equation in standard form. A is 1. B is a negative 2. Negative 2 is the number in front of the x, and C is a negative 4. The opposite of a negative is a positive. Plus or minus, I'm substituting a negative 2 into a formula that is being squared. So notice I put it in parentheses. It matters especially if you are going to use a calculator. All over 2 times 1. Again, the orders of operation tell us that we do what's underneath that grouping symbol first. A negative 2 times a negative 2 is a 4. A negative times a negative is a positive. 4 times 1 is 4. Times 4 is 16. 2 times 1 is 2. 2 plus or minus the square root of 20 over 2 equals x. Now, I do notice that my factors of 20, 1 and 20, 2 and 10, 4 and 5, lend us to a perfect square number. 4 is a perfect square number. Perfect square numbers, remember, are numbers that when you multiply them by themselves, it equals that number. So the factors are the same. The square root of 4 then is 2 over 5. Now, because I'm dividing this by 2, I'm going to rewrite it as 2 separate fractions so that I don't mess up when I start dividing. 2 divided by 2 is 1. 2 divided by 2 is 1, radical 5. And now we have simplified our problem. I do want to do another example. And in this case, our example is going to lend us some complex or non-real answers. And we'll talk about that in just a moment, the nature and what kind of answers we're going to have. Again, solve using the quadratic formula. I've got to make sure that it's in standard form. So I am going to have my x squared, my x, and my 7 all on the same side. A is 1, B is a negative 4, C is 7. X is equal to the opposite of B, so the opposite of a negative is a positive, plus or minus the square root of, again, B squared is negative, so I'm going to put it in parentheses, quantity squared, minus 4 times 1 times 7, extend my radical, all over 2 times 1. The orders of operations say I have to do what is in my grouping symbols first. 4 times 4 is 16. 4 times 1 is 4 times 7 is 28, divided by 2 times 1. 16 minus 28 is going to give me a negative 12 underneath that radical. And if you recall, the perfect square then is 4 times 3, and the negative is a negative 1. The definition, the square root of a negative 1, is an imaginary number. 4 plus or minus the I, the square root of 4 is 2 square roots of 3, and I'm going to put my fractions, the first number, write it as a fraction. My second number, write it as a fraction because it's everything over the 2 times 1. 4 divided by 2 is 2. 2's divide out, giving me 1i radical 3. So x equals 2 complex numbers. I want to show you what you would have to do if you had an example and it's not equal to 0. If it's not equal to 0, then you're going to have to subtract and move everything over so it is equal to 0 and have it in standard form. We have looked at a couple of different problems where we've had real numbers, we've had imaginary numbers, which is this I business that we were talking about, those complex numbers, and it all comes from the discriminant. The discriminant is the part of the quadratic formula underneath that radical, the b squared minus the 4ac. You're having the square root. If you're taking the square root of a positive number, that square root is plus or minus. So that's 2 answers, and they're real because it's a positive number. If you have the square root of a negative number underneath that radical, there are 2 answers, but they are non-real complex numbers. We have another possible scenario. If you have it equal to 0, if the b squared minus 4ac equals 0, then plus or minus 0 is the same answer as whatever your opposite of b over that 2a is, which lends you to 1 answer. So the discriminant will tell you, the discriminant is the stuff underneath, and we have 3 possible choices. When the discriminant is positive or greater than 0, you're going to get 2 real answers. If your discriminant is negative, you're going to get 2 non-real complex numbers. And if it is equal to 0, you're going to get 1 real solution. You do not have to work out the whole quadratic formula to determine the nature or how many your answers are. You just have to use that discriminant. So our example then says, for each of the quadratic equations, find the discriminant to determine the nature of the roots. X squared plus 4x minus 21 equals 0 is our equation. The b squared minus the 4ac is all I'm worried about to determine the type and how many I'm going to have. Again, our a is the number in front of the x squared, b is the number in front of the x, and c is the constant. 4 squared minus 4 times 1 times the negative 21. 16 plus 84 is going to give me a positive answer. I don't have to necessarily find the discriminant by adding these two together. I could. This is going to be a positive answer, so I know I'm going to have 2 real answers or 2 real solutions.